All right, the next thing I want to do is I want to actually fill in, there's one gap that I've left inadvertently, and these are words that I've used before, but I want to completely explain row echelon form in what's called a reduced row echelon form. So reduced row echelon form, which sometimes I'll write RREF. And these are just different words that can describe a matrix after it's been simplified a little bit. So let's say that you have a matrix, and I'm not going to worry too much about what the matrix is that we start with, but I just want to mention there's three properties for row echelon form and reduced row echelon form. Reduced row echelon form is a little easier to describe. It's basically as simplified as a matrix can get. So if you were to have a matrix that would look like this: 1, 0, 0, 0, and then 0, 0, 0, 0. This is in reduced row echelon form. So this is in reduced row echelon form. And reduced row echelon form, again, just means that the matrix is as simplified as it gets. So the first thing that we want is that the first non-zero term, so the first non-zero term in any row, so the first non-zero term in a row is a 1. Okay, so notice that the first non-zero terms are both 1s. So that's the first step. The second step, what makes it in reduced row echelon form, is that the leading terms so I want to just explain this using language as much as I can before writing too much, but the leading terms go down in a diagonal. So if you have a column that has a leading term in it, it's below all the other columns that have a leading term in it that are to the left of that column. So in other words, you want the leading ones to go in a diagonal fashion as much as possible. Okay, so you want them to go diagonally. So the leading terms are sorted diagonally. You want them to go, what I mean by that is that you want them to be in the order from top left to bottom right. If I were to switch row 1 and row 2, if we were to switch those two rows, that would no longer be in reduced row echelon form because it's in kind of the opposite order. You would have a 1 here and a 1 here, and that's the wrong direction. So you want the 1s to slant down and to the right. And then the third quantity, or the third characteristic that makes this reduced row echelon form, is that all entries in a column, this column containing a leading 1. So if you have a column that has a leading 1 in it, so here's a 1, but it's not a leading 1, it's not the first non-zero term. So if you have a column that has a leading 1, all the other entries in that column need to be 0. Okay, so all the other entries in the column are 0. So, for example, this matrix is in reduced row echelon form because the 1s go down and to the right. The first non-zero term in each column is a 1. And for the columns with the leading 1s, the other terms are 0. Okay, so those are 0 there. So that is reduced row echelon form. And let's just talk about some examples here. If I were to take 1, 1, 1, 1, 0, 0, 1, 0, and 0, 0, 0, 1. I'm sorry, there's one more thing that we want for reduced row echelon form that I forgot. And this is important. This is actually kind of a corollary of number 2, but all non-zero rows are at the bottom. So all non-zero rows are at the bottom of the matrix. Okay, so sorry, I forgot that small detail there. That's kind of, that happens naturally if you do the, if the leading terms are sorted diagonally. But for this matrix, if you have 1, 1, 1, 1, 0, 0, 1, 0, 0, 0, 0, 1, this is not in reduced row echelon form because you have columns, so the problems are right here, because you have values that are in a column, the column containing a leading one, and those values are non-zero. If you make those values 0, so if you were to make those values 0, this is in reduced row echelon form. Okay, so that is reduced row echelon form. Now, one other thing is row echelon form. If number 1 and number 2 are true, but number 3 is not, then the matrix is in row echelon form. Okay, row echelon form can be good enough for applications. You don't necessarily need to simplify the matrix as much as possible in order to solve a system, say. So for example, if you were to take, if you were to look at the matrix, let's just do a square matrix here, 0, 0, 1, and this is going to be a square matrix, and we'll augment it with something so that this is a system of 3 equations, 3 unknowns. But let's say we were to have 1, 2, 3, 0, 1, 4, 0, 0, 1, and then our system is going to be 5, 3, yeah, 5, 14, 3. So if that's going to be your system here, this is good enough to solve the system. You don't actually need to go through and do the other 2 steps or the other 3 steps for simplifying and putting this in reduced row echelon form, because all you really wanted to do when you have these augmented matrices is solve the system. You know that x3 is going to be 3. You get that from the bottom equation. The second equation tells you that x2 plus 4x3 is 14. In other words, x2 plus 12 is 14, so x2 is 2. And then if x2 is 2 and x3 is 3, then you know that this top equation, x1 plus 2x2 plus 3x3 being 5, tells you that x1 plus, let's see, 2 times 2 is 4, 3 times 3 is 9, equals 5. So x1 is going to be -8. So there's your solution to the system, right? x3 is 3, x2 is 2, x1 is -8. So there's your solution. And you didn't need the matrix to be in reduced row echelon form in order to solve the system. Row echelon form was good enough. So this requirement that the values in the column that are not the leading ones needing to be 0 isn't a strict thing in order for this matrix to be useful. But certainly in general, the more simplified it is, the easier it'll be to work with. Okay, so that's reduced row echelon form and row echelon.